Good evening, Lamai. Today we are going to discuss about the secondary interactions. Right? Secondary interactions. Secondary interactions means those are the interactions among molecules. So these are also known as intermolecular forces. Right? Intermolecular interactions. So actually secondary interactions are involved when you are to connect molecules together. Right? Before this topic, we have discussed about the primary interactions now. There were three kinds now. Covalent bonds, right? Ionic bonds and the metallic bonds. Now we are up to secondary interactions. With primary interactions, normally atoms are stick together with the use of primary interactions. But when it comes to secondary interactions, those are the reasons for the connection of molecules. Right? So molecules are connected by the intermolecular forces or the secondary interactions. So let's discuss about them. In our A-level syllabus, we are going to study about 5 types of secondary interactions. There are 5 types of secondary interactions appearing in our A-level syllabus. Right? Let's discuss about them one by one. Right? The first kind. So there is a type of secondary interaction called as ion-dipole interactions. Ion-dipole interactions. Then the second type, dipole-dipole interactions. Dipole-dipole interactions. Right? So there we'll discuss about some special kind called as hydrogen bonds, which is also coming under the dipole-dipole interactions. Then the third type, ion-induced dipole. Ion-induced dipole interactions. Then we have dipole-induced dipole interactions. Ultimately, we are going to study about the induced dipole interactions, or which is known as the London forces or London dispersion forces. London dispersion forces. Right? So these are the 5 types of secondary interactions we are going to study. Among these kinds, dipole-dipole interactions, the ion-induced dipole interactions, dipole-induced dipole interactions, and the London forces. Right? Sorry, not these three, right? These three. Actually, these three star-marked interactions are also known as van der Waals forces. Also known as van der Waals forces. Van der Waals forces, right? Van der Waals forces. I'll write it here now. Right? Dipole-dipole interactions, dipole-induced dipole interactions, and the London dispersion forces are also known as van der Waals forces. Right? The forces involving the ions and the hydrogen bonds comes under van der Waals forces, right? But the other three stuff, right? Basically, van der Waals forces are the weakest kind of interactions among molecules, right? Those are these three. This one, and this one, right? So these 5 types of forces or secondary interactions are to be studied under the A-level syllabus, right? So when we are looking at these names of these 5 types of secondary interactions, we can clearly see some names, some sections appearing repeatedly. See, the ions, dipoles, and the induced dipoles. These are terms appearing with most of the secondary interactions. Let's discuss a bit about these things. What are these ions, dipoles, and induced dipoles? Right? The ions, dipoles, and induced dipoles. So it is, sorry, this is induced dipoles, right? Induced dipoles. Right? Ion-induced dipole interactions, right? Okay. What are these kinds? The thing is this, right? Basically, the charged particles, particles with complete charges are known as ions, right? Ions are the particles with complete charges. Particles with complete charges are known as ions. See, you will come up with cations as well as anions, the sodium plus, Cl minus. Those are ions. Particles with complete charges are referred to as ions. Then what are these dipoles? What are these dipoles? The dipoles are the polar molecules. Dipoles are the polar molecules. Those are molecules which are polar. So polar. Right? Polar molecules are known as dipoles. So if you need some examples, right? The HBr is kind of a dipole. It's a polar molecule, right? Which is with a net dipole moment. Net charge is zero, but partial charges are appearing there. So another one, water, another polar molecule, right? Your negative pole is on the oxygen, the positive pole is between the 2 hydrogens. The polar molecules are referred to as dipoles. So as a whole, they won't possess any charge. Net charge is zero. HBr, H2O. The net charge is zero. But those are with some positive delta, negative delta poles, polar molecules. Asymmetric electron distribution can be seen with this, right? So electron distribution is not symmetric, right? Those are the dipoles, simply the polar molecules, molecules with a net dipole moment, right? Let's discuss about what are these induced dipoles. Induced dipoles. Induced dipoles. Right? Induced dipoles are actually non-polar molecules which will induce dipoles, right? Which will induce dipoles. Normally those are the non-polar molecules. See, if you need an example, right? So if you think of something like argon, nonpolar species. It could be molecules or species. Right? Let's think of the argon. Argon is a symmetric electron density. Symmetric electron density. Right? But it can induce some dipoles. Like this. Right? When kind of a negative charge is applied here and kind of a positive charge is applied here, the electron density will attract towards the positive charge and more density will approach there and less density here. So you will create a dipole. That is how the induced dipoles are created, because of the polarizability of these non-polar species. Right? These are the induced dipoles. Right? So those will be created with the use of their polarizability. Right? So we can have much more the CO2 or any kind of non-polar molecule can be referred to as an induced dipole. Right? Okay. Those are the major three terms appearing with these secondary interactions. Right? So studying this is very easy, Lama. Right? Let's think of this. So if you are thinking of some water where you have NaCl dissolved in it, some NaCl solution, sodium chloride solution, think of that. In such a solution, you would see the appearance of water molecules near to the sodium plus particles as well as Cl minus particles. Right? Na plus particles will be surrounded by H2O molecules. Cl minus particles will be surrounded by water molecules. They are between the Na plus and the water. Between the Na plus and the water, right, you would observe a formation of ion-dipole interaction. The Na plus is kind of an ion. Water is kind of a polar molecule, that means a dipole. So between those two, ion-dipole interactions form. Right? Like that. So between two dipoles, you will form dipole-dipole interactions. That means between two molecules, polar molecules, dipole-dipole interactions will form. Right? Between a ion and a non-polar guy, ion and a non-polar molecule. Now, as non-polar molecules are referred to as induced dipoles. Between an ion and a non-polar molecule, the ion-induced dipole interactions will form. Like that, very easily, you can identify the type of second interaction among species. Right? Okay. So with this knowledge, let's discuss about these second interactions one by one. Right? Okay. Let's start with the ion-dipole interactions. Ion-dipole interactions. Right? As the name suggests, these are the interactions among ions and dipoles. Ions means what? Ions means cations or anions, positive particles. Right? Positively charged particles. Or negatively charged particles. Those are the ions. Dipoles, those are the polar molecules. Polar molecules. So if you are to think of kind of interaction forming among positively charged particles or negatively charged particles with the polar molecules, then those are referred to as ion-dipole interactions. Those are ion-dipole interactions. Right? See, let's come up with an example. Right? Let's come up with an example. Right? Think of a sodium chloride aqueous solution. Sodium chloride aqueous solution. So sodium chloride aqueous solution is formed by dissolving the sodium chloride, by dissolving the sodium chloride in water. Dissolving sodium chloride in water. So in an aqueous solution of sodium chloride, you have the sodium chloride and the water, right? So if you are to add some, right, NaCl solid to water, right, a sodium chloride solution will form, right? A sodium chloride solution will form, right? So what happens there? There you have these ions here, and you have the polar molecule here, water, kind of a polar molecule. We can say it has a dipole. So ion and dipoles are there. So you have dipoles now. So you have the negative pole here, positive pole here. Substance with two poles, dipole. So if you are to mix these two things together, what will happen? This Na plus ions will be surrounded by the negative pole of your dipole. So it will be like this. The negative pole is oxygen. The Na plus ions will be surrounded by the negative pole of your dipole. Right? It's a negative pole now. Right? So there will be interaction between this negative pole of dipole and the positively charged ion. Actually, that interaction is known as what? Ion-dipole interaction. Ion-dipole interaction. The interaction between an ion and a dipole. An ion and a dipole. It's a dipole, right? Species with two poles. The interaction between an ion and a dipole is referred to as the ion-dipole interaction. So not only sodium, but also the chlorine, the negative charge, will also surrounded by the water molecules with the use of its positive terminal. For the negative charge, the positive terminal of water will approach. Opposite charges will attract, right? That is simply like that. So towards here, the positive pole approaches of your polar molecule. So there also kind of a second interaction will form. Ion-dipole interactions. Ion will be attracted by a polar molecule. Right? These are the ion-dipole interactions which will appear in a sodium chloride aqueous solution. So this particle ultimately can be referred to as the Na plus aqueous, the iron and water molecules, and with connected with ion-dipole interactions, the Cl minus aqueous. So in a solution, in a sodium chloride solution, this is the bond in nature. The secondary bonds appear like that, right? Those bonds are referred to as ion-dipole interactions, right? So let's discuss more about these interactions. Basically, we can comment on the strength of these ion-dipole interactions too. The strength of ion-dipole interactions, right? Let's discuss about that thing as well. The strength of ion-dipole interactions, right? Let's write it here. The strength of ion-dipole interactions. Strength of ion-dipole. I'll write it as dP, ion-dipole interaction. Actually, strength of ion-dipole interactions will depend on the charge density. Due to the charge density of the ion, the charge density, Q over R ratio of ion. Right? If the charge density of your ion is high, that means your polar molecule will attract heavily to that ion, making it a strong ion-dipole interaction. Right? So if the charge density of sodium is high, right? So this negative pole, the opposite pole, will attract heavily towards this your cation. So the ion-dipole interaction strength will be high. If the charge density of your anion is high, the positive pole of the dipole will attract heavily towards your anion. So strong ion-dipole interaction will form. So ion-dipole interaction strength will depend on the charge density of the ion. Right? So as example, see, right? If you think of ion-dipole strength between the sodium plus ion and the potassium plus ion, can you comment on the ion-dipole interaction strength of Na plus Aq and the K plus Aq? Can we comment? Right? Let's see. Let's try to come up with such idea. Right? Let's try to comment on ion-dipole interaction strength. So basically, ion-dipole interaction strength is actually high for sodium plus compared to the K plus. The reason is clear, no? Why is that? Both the cations are with same charge. Right? Both the cations are with same charge. Na plus Aq, right? Na plus Aq compared to K plus Aq. Both the cations are with same charge, but the radius is smaller with the sodium plus ions. So smaller the radius, greater will be the charge density. So charge density is high with the Na plus Aq than the K plus Aq. So that ion-dipole interaction strength of sodium plus Aq is greater than the K plus Aq. Like that, you should be able to comment, right, on the ion-dipole interaction strength with the use of the charge density of cations as well as the anions, right? The charge density of ions matters for the ion-dipole interaction strength. Right now? Okay, that is the idea, right? This is all what you should know, right? So you can draw the picture here, right? This picture as well as this one, right? With some example, right now. Okay, that is all about the ion-dipole interactions and its strength. So you normally, when you are trying to dissolve some ionic compounds in water in some polar solvents, right, you will observe the formation of ion-dipole interactions. Formation of ion-dipole interactions, right? If you need some other example, see, let's come up with another example for the ion-dipole interactions. Right. See, another example for this one. Right. KOH dissolves in alcohol. Right. KOH dissolved in alcohol. It is also known as alcoholic KOH. See, the KOH contain ions. With KOH, ions are appearing. Ionic compound means ions. Right? Alcohols. Right? So I'll come up with some alcohol, kind of methanol kind of stuff, right? Ethanol, right? So this is kind of an alcohol. Alcohol. See, it is also a polar reagent. We have minus terminal here, some positive terminal here. Alcohol. This is actually ethanol, right? Ethanol. It's a polar molecule. Means it's a dipole. So if you are to mix these two things together, right, you will end up with ion-dipole interactions. So K plus ions will be surrounded by the oxygens. I'll write it as C2H5, this stuff, right? There you see the formation of ion-dipole interactions. Right? These are the ion-dipole interactions. In alcoholic KOH, the OH minus ions will be surrounded by the solvent, the positive terminal of a solvent. Right? So ion-dipole interactions. Right? This is the alcoholic KOH. Right? Where you have K plus and the OH minus surrounded by alcoholic solvent. Right? So these are the ion-dipole interactions. Another example. Right? So you can copy this one as well. Right? Ion-dipole interactions are the type of interactions appearing between ions and polar molecules. Ions and polar molecules, right? So opposite charge of your dipole will attract to the ion, right? If your ion is positively charged, the cation, so the negative pole of your dipole will attract to that. If your ion is with a negative charge, it's an anion, then the positive pole of your dipole will attract to that, right? That is how the ion-dipole interactions are to be formed, and their magnitudes will be also given by this expression. Greater the charge density of your ion, greater will be the ion-dipole interaction strength. Here, when it comes to these two guys, surely the charge density is greater with this one, because both are carrying 1 unit of charge, the plus 1 or minus 1 unit of charge. The Coulombic charge is same, right? 1 unit of charge. But this one is smaller than this one. This one is with 3 electronic shells, while this one is with only 2 electronic shells. 10 electrons, this is 18 electrons. So this one is smaller. Smaller you are, your charge density will be high. So the solvent molecules will greatly attract towards the OH minus compared to K plus. So the ion-dipole interaction strength will be greater with the OH minus solvent and compared to the K plus with the solvent, right now. So that is all about the ion-dipole interaction strength, right? So this is all about the ion-dipole interactions, right? Let's discuss about the second kind of secondary interaction. Second type, dipole-dipole interactions. Dipole-dipole interactions, right? Dipole means it's a polar molecule. Again a dipole, another polar molecule. So dipole-dipole interactions are the interactions appearing among polar molecules. Dipole-dipole interactions. Interaction among polar molecules, right? Okay, right. Let's discuss some examples, right? Some examples, right? Take the HBr. Among HBr molecules, you would see the presence of dipole-dipole interactions. See, so the HBr. So you have H and a Br like this. You have another H and a Br. See, both are polar molecules carrying some dipoles. So positive pole is here, negative pole is here for the HBr, because Br is more negative than the hydrogen. So the electron cloud will attract towards the bromine, making it the negative terminal. Positive pole is here, negative pole is here. So between this negative and the positive poles, there would be an interaction, electrostatic attraction, which is known as the dipole-dipole interaction. So this thing is known as dipole-dipole interaction. Right now, among polar molecules, dipole-dipole interactions appear, right? Let's discuss another example, right? Let's take the formaldehyde. Right? Formaldehyde is this HCHO, that is the compound. Right? Let's concern about that thing. Formaldehyde. So this is a formaldehyde molecule. So this is a polar molecule. So you have a negative pole here and a positive pole here. So you can discuss about the net dipole moment. Net dipole moment will be towards here. So the negative pole appears here and positive pole appears here for the HCHO. So the HCHO molecule will combine with another HCHO molecule with the use of dipole-dipole interactions. See, these opposite charge poles will get attracted via electrostatic attractions, right, which are known as the dipole-dipole interactions. Right? So polar molecules will combine together with the use of dipole-dipole interactions. Right? Okay. So name suggests who are the guys which will participate in forming this interaction. The dipole-dipole. Dipole means polar molecules, another dipole, another polar molecule. Dipole-dipole interactions. Right? These are some examples. But normally, with these dipole-dipole interactions, with normal dipole-dipole interactions, right, their strength, the strength is kind of the strength of this bond. I'll mark it here. Normally, the strength of a dipole-dipole interaction is between 0.5 to 15 kilojoules per mole. This is strength of a normal dipole-dipole interaction. Right? That kind of a strength is there. Right? That is what we normally concern as dipole-dipole interactions. Right now? Okay. Let's discuss about the next one. Right? So, next subtopic we are going to discuss is actually hydrogen bonds. Let's discuss about this. Hydrogen bonds. Right? So actually hydrogen bonds is also coming under dipole-dipole interactions. But those are the strongest dipole-dipole interaction we would observe. The hydrogen bonds are the strongest dipole-dipole interaction kind. Hydrogen bond. Right? Hydrogen bonds are also kind of interactions appearing among polar molecules. Right? So kind of secondary interactions. Appearing between or appearing among polar molecules. So it's a kind of dipole-dipole interaction. But it is the strongest of them. Kind of second interaction appearing among polar molecules, and it is the strongest. It is the strongest. among dipole-dipole interactions. Right? Normally, strength of hydrogen bond, right, varies in the range of 4 to 40 kilojoules mole. The dipole-dipole interaction normally comes with 0.5 to 15 kilojoules mole, no? But here normally the strongest, right, coming up with kind of 4 to 40 kilojoules mole. The strength is that for the hydrogen bonds, right? Okay, let's discuss how these hydrogen bonds are formed. How these hydrogen bonds are formed, right? Or the definition of hydrogen bonds, or how these special kind of bonds are formed, right? The thing is this, right? So what is this thing, right? Definition of hydrogen bonds. So if a molecule with hydrogen which is connected to a highly alternative atom, so this atom with very high affinity. If you have a molecule with a hydrogen which is connected to a highly alternative atom, means fluorine, oxygen, chlorine, or nitrogen, atoms with high affinity, right? If hydrogen connected to an atom with high affinity, such a molecule is there, and if another molecule is there with a highly affinity atom carrying some lone pair, hydrogen atom carrying some lone pair. If you see the appearance of these two guys closely together, right? Chlorine is not acceptable here. If you see the appearance of these two guys closely together, there will be a bond between these guys, which is known as the hydrogen bonds. Right? Is known as the hydrogen bonds. Hydrogen bond. Right? Its strength is between 4 to 40 kilojoules mole. Right? This is how the hydrogen bonds are formed. If you are with a molecule with hydrogen which is connected to a highly affinity atom, and if you are with another molecule with a highly affinity atom with a lone pair, then if those two guys are close together, if those two guys are connected, then that is due to a formation of a hydrogen bond. That is the idea. Normally these bonds are very stronger than the other dipole-dipole interactions. These bonds are very strong than the other dipole-dipole interactions. Right? Let's discuss why it is so. Right? The idea is this. Basically, if you have a hydrogen and a high affinity atom like this, so this bond will be greatly polar. Because this is very high affinity atom. So electron densities will be greatly attached. The sharing pair of electrons will be greatly attracted towards this atom, so that you will create a greater positive delta here and a very greater negative delta here, right? Because as the polarity is very high, as it is a very highly attractive atom, you will create a very great positive delta here. On the other hand, as these electrons are highly attracted to us here, because this is a highly attracted atom, so the electron density of this thing is very high, creating a greater negative delta here. So attraction between these two things will be the greatest among the dipole-dipole interactions. Attraction between these two will be the greatest among dipole-dipole interactions, which is known as hydrogen bonds. Right? Actually, these things are named as hydrogen bonds because the hydrogen is the one which connects these two masses. Hydrogen is the one which connects these two masses. That is why this is referred to as the hydrogen bond. Right? Between these two masses, the hydrogen is appearing. So hydrogen will connect these two masses. Right? Hydrogen will combine these two masses. That is why this is known as the hydrogen bond. Right? Normally, when regarding a hydrogen bond, right, this compound, the compound bearing the hydrogen involving in the hydrogen bond, is known as the hydrogen donor. This thing is known as the hydrogen donor. Hydrogen donor of the hydrogen bond. This is referred to as the hydrogen acceptor. Hydrogen acceptor of the hydrogen bond. This guy is the one which will donate the hydrogen, and this is the one to accept the hydrogen, like this. Hydrogen acceptor. Right? So anyway, hydrogen bond is formed with this kind of a structure, where hydrogen is at the center and two alternative atoms are connected to that hydrogen. That is why this is referred to as the hydrogen bond. Right? Okay. So when we are to discuss about the hydrogen bond, always these three atoms lies in a straight line. These three atoms are linear. 180-degree angle. 180-degree angle around the hydrogen. Right? So in a hydrogen bond, right, the alternative atom, hydrogen, and the other alternative atom. These atoms are linear. These atoms are linear. That is first thing you should know about the hydrogen bonds. Right? Here, the three things are linear. Secondly, it's very important to note that here, right, you can come up with FOCl in all the atoms, right, as the alternative atom here, but not here. As the alternative atom here, as the hydrogen acceptor, only the fluorine, oxygen, and nitrogen can appear there. Right? Even though the alternative of fluorine is greater than nitrogen, still fluorine can't appear here for the hydrogen bonds. Right? If you want to know about the alternatives, right? So the alternative is like this now. So atom and the alternative. So fluorine is with 4.0, oxygen is with 3.5. The third place belongs to chlorine, it is 3.1. Fourth place belongs to nitrogen, which is 3.0. Right? These are the alternative values of the atoms with greatest alternativity. even though chlorine gets the third place with the trinity, right? As a hydrogen acceptor, chlorine is not acceptable, right? You should know the reason there, right? Chlorine is not accepted as the electronegative atom. Of hydrogen acceptor. Right? Why is so? Why is that? The reason is, Lamayan, when chlorine is here, as chlorine is considered as a third row element, the distance between the chlorine and the hydrogen would be larger, so that the bond strength will be smaller and bond comes under this range of hydrogen bond. As chlorine belongs to the third row, not like these guys are second row guys, but chlorine belongs to the third row. So when you have a third row element here, the distance between the chlorine and the hydrogen is somewhat large. So greater the distance between the two atoms, or greater the bond distance, smaller will be the bond strength. So the bond strength decreases so that it won't comes under this range. It is less than 4. Bond comes under this range when the chlorine is here. So chlorine is not accepted at the hydrogen acceptor side, right? It's not accepted as the hydrogen acceptor side, right? The reason is Cl H bond distance is high, hydrogen bond distance is high, so that the bond is weak, not that strong. So hydrogen bonds are the strongest kind of second interactions. But when chlorine at the hydrogen acceptor side, that is what happens, right? Okay, so those things you should know, right? So another simple thing, and here most of the occasions the FOCl appears, and very rarely some other element could also appear, so that I'll write it as other as well, right? This is all about the formation of hydrogen bonds, right? And this rule, this definition is also known as the Fonkel rule. It's also known as the Fonkel rule. F-O-N-C-L rule, Fonkel rule. This definition is known as the Fonkel rule. Keep in mind, right, this is known as a Fonkel rule, not because the electricity order is like this. The electricity of chlorine is higher than the nitrogen, right? This is referred to as Fonkel rule, not because of the electricity varies like this, right? But because of the possibility of forming hydrogen bonding, ability of participating in hydrogen bond is greater with nitrogen than the chlorine. Ability of participation in the hydrogen bond, in hydrogen bonds, is greater with nitrogen than the chlorine. That is why nitrogen comes first before the chlorine. That is why this rule is known as Fonkel rule, not because of the electricity values, right? The third place of the electricity belongs to chlorine, not for the nitrogen, right? But this is referred to as Fonkel rule because nitrogen is with a greater ability of participation in hydrogen bonds than the chlorine. This chlorine is not accepted here. Nitrogen is accepted. at the both sides. Right? This is the Fonkel rule. Right? Let's discuss some practical examples and see how the Fonkel rule applies there when forming hydrogen bonds. Right? Let's go to some practical examples. Right. Okay. I'll erase this thing. I come with some examples. Here. Right? Examples. For hydrogen bonds. Right? Let's discuss some examples. Okay. First thing, water. Among water molecules, the hydrogen bonds are present. See, this is a water molecule. Right? So you have these lone pairs. Right? This is a water molecule. Right? And draw like this. Okay, right. Okay. So this will be connected to other water molecules. See, this is another water molecule. This is another one. So, few more water molecules, right? Even this one. Right? So, these water molecules are connected via hydrogen bonds. This lone pair will approach this hydrogen, which is the positive delta. This lone pair will approach this hydrogen. Right? The idea is clear now? Right? This kind of positive delta, negative delta. Right? So, those things appear now. Those will be approached by these guys. So this will mean attract this, and this thing will attract here. So one water molecule can form 4 hydrogen bonds. Here, this one water molecule can form 4 hydrogen bonds. Right? That is very important. Note that. Right? One water molecule can form 4 hydrogen bonds. Right? One H2O molecule can form 4 H bonds. Right? So you should be able to identify the structure here. See, this is the lone pair, and this is the hydrogen, and this is the other electronegative atom. So you see, with this type, right, you have a hydrogen and an electronegative atom. Hydrogen and electronegative atom, which will be connected to another electronegative atom from another molecule by its lone pair. So you have another electronegative atom with another molecule, and you have a lone pair. So these things will connect via hydrogen bonds. So here as well. So this is the electronegative atom, this is the hydrogen, electronegative atom and the hydrogen from one molecule. Then from the other molecule, you have electronegative atom with a lone pair. Electronegative atom with a lone pair. So those will be connected via a hydrogen bond. So like that, if you are think of a one water molecule, as it is with two lone pairs and two positive delta hydrogens, right, that water can form 4 hydrogen bonds. One water molecule can form 4 hydrogen bonds. That is very important to note that. One water molecule can form 4 hydrogen bonds. Right now? Okay. So actually this thing happens like this. So when these electrons are heavily attracted by the oxygen, then only this lone pair tends to given away to the other molecule. When you get some greater electron density from here, from 2 electrons, when you gain some greater electron density of 2 electrons, then this oxygen tends to release some 2 electrons to the outer molecule as well. When these two guys are attracted heavily towards here, then these two things are released. Oh, one can say like this. When these two things are released, this oxygen feels some electron deficiency of 2 electrons, then these two things will be attracted heavily. When these two things are released towards this positive delta hydrogen, oxygen will feel some great electron deficiency of 2 electrons, so that it will greatly attract these 2 electrons towards it to create this greater positive charge, positive delta here. So anyway, lone pairs and bonds are related. When you give off some lone pair, then only 2 electrons of the sigma bond will be greatly attracted. When you release this, you attract here heavily. When you attract the things heavily, you release this. Both happen simultaneously. Like that, one water molecule is able to form 4 hydrogen bonds. Right? It's a water molecule, right? Which is drawn in black color. Right? Okay. Right. Let's discuss about another example for hydrogen bonds. HF. Among HF molecules also, you can see the presence of hydrogen bonds. See, right? This is kind of HF molecule. HF molecule, right? With the fluorine, you are with these lone pairs, right? So you have a positive delta here, negative delta here, as these electrons are attracted towards the fluorine, which is more attractive than the hydrogen, right? And this HF molecule will be attracted to another HF molecule, right, with the use of a hydrogen bond. So when it comes to this HF molecule, this is negative delta, this is positive delta. So these two things will get attracted. These two guys will get attracted. And what about this? So this lone pair will also be released to another HF molecule. So you have a greater positive delta appearing here because the electrons are attracted by this fluorine. You have a greater negative delta here. So this pair will be released here. See the linear nature around hydrogen, linear nature. right? Anyway, again you see two hydrogen bonds can be formed by an HF molecule. Two hydrogen bonds can be formed by an HF molecule, right? This is a HF molecule, right? It can form two hydrogen bonds. One HF molecule can form two hydrogen bonds. Two hydrogen bonds. Right? One may think that HF is able to form four hydrogen bonds because three lone pairs are appearing. No, that is not the case, right? That is not the case. Right? When the electron density is attracted heavily from the HF bond, only one electron density is more keen to get released. When only one electron density is more attracted towards the fluorine, only one electron density is more keen to get released. Not all the guys. Because when fluorine feels some great electron density, as it greatly attracted these two electrons of the covalent bond, then it can release only one electron density towards the other hydrogen bond formation, right? So only one of the lone pairs out of three will participate in hydrogen bond in there. So only two hydrogen bonds can be formed by a single HF molecule, right? No, that's very important. No? Third case, right? Let's discuss about another example. NH3, ammonia. So ammonia is also able to form some hydrogen bonds among those molecules. See how it formed. So when it comes to ammonia, right? When it comes to ammonia, right? This is the ammonia molecule, no? NH3. This is the ammonia. Right? This is ammonia. Right? So you have a negative delta here. Because of attraction of these electrons from hydrogens, you have a negative delta here. So that this electron pair is keen to be donated. So you have that situation, right? A22 atom and a lone pair. A22 atom and a lone pair. Right? That lone pair is keen to be donated towards a highly positive hydrogen coming from another ammonia molecule. Right? So you would see this. I'll come up with a different color, right? Right? So this hydrogen is negative delta, this is positive delta. So you would see the formation of hydrogen bonds between these two. Right? So you have a nitrogen with a lone pair, A22 atom with a lone pair, and you have a hydrogen connected to a A22 atom like this. So there will be attraction between the opposite charges, which is known as the hydrogen bond. See, how it appears. Thing is linear. Right now? Okay. When one pair of electrons are going to be donated like this for a hydrogen bond, nitrogen feels some electron deficiency of pair of electrons, so that it will attract one of the pairs in this bond heavily towards nitrogen. Not all the things will be attracted heavily, but one of the electronic pair, the shared pair, will be attracted heavily, creating a greater positive delta there. So that guy can then involve in hydrogen bonding, as it is created a greater positive delta with another molecule. See, you have a nitrogen and a lone pair. So here you can think of a hydrogen bond, as this nitrogen is negatively charged, coming from the electron densities of hydrogens, right? So kind of hydrogen bond will form here, right? So one ammonia molecule is able to form only 2 hydrogen bonds, right? One ammonia molecule can form 2 hydrogen bonds. One ammonia molecule can form 2 hydrogen bonds. See? So one can think that one ammonia molecule can form 4 hydrogen bonds, as these 2 hydrogens are also appearing. No, that is not the case, right? Because only one electron pair is released towards the hydrogen bonds now by the nitrogen. So nitrogen only feels deficiency of one electron pair. As only one is released, deficiency of one electronic pair will be felt by the nitrogen. So that from only one single bond, the electrons are heavily attracted to form a greater positive delta. These are also positive delta charged, but not that much. This kind of greater positive delta is needed to form the hydrogen bond, to do a heavy attraction, right? So that is done by only one NH bond, because only one lone pair is on the nitrogen, right? So ammonia is able to form only 2 hydrogen bonds among molecules. One ammonia molecule is able to form only 2 hydrogen bonds, right now? So that is about the hydrogen bonding in ammonia, right? Okay. Let's discuss the strength of the hydrogen bonds of these 3 guys. Let's discuss about the strength of hydrogen bonds among these 3 guys. Right? Strength of hydrogen bonding among the both HF and NH3. Right? If you are to compare the strength of hydrogen bonds. Now, when you are with a great electronic difference, when you are with a greater delta, right, the attraction will be heavy. When you are with a greater deltas, greater charges on atoms, the attraction will be heavy. The hydrogen bond strength will be high. So the greatest positive and the negative deltas will appear with the HF bond. Because with the HF, you would observe the greatest electronity difference. You would observe the greatest electron difference between the HF. The hydrogen is 2.1. Between the HF, you would observe the greatest electron difference, right? So that the strongest hydrogen bond will form between the H and F. Next, the H and O. Thirdly, between the H and N, right? So strength of hydrogen bonds depends on the electron difference. of the two participating atoms, right? The point is, when delta X difference is high, strength of hydrogen bond is high. So that the things will vary like this. So the HF hydrogen bond is the strongest, then the H2O hydrogen bond, the least among three is HN hydrogen bond, right? The strength of hydrogen bonds vary like this among the HF, H2O and the NH3, right? Next one. Let's discuss about the melting points of these things or the boiling point of these things. Boiling points. Or boiling point variation. Between the H2O, Hf and NH3. Now, the boiling point variation is given as the H2O is with the greatest boiling point, the 100, and HF is with the next highest, and this the NH3 is with the least boiling point. Even though the hydrogen bond strength varies like this, HF is not the one with the greatest boiling point. HF is not the one with the greatest boiling point. The greatest boiling point is with H2O, not the HF. So something to consider, something to learn there, right? The thing is this variation is due to actually number of hydrogen bonds one particle can form. Is due to number of hydrogen bonds one particle can form, not due to the strength of the hydrogen bond. So actually boiling means at the boiling point, what happens? At the boiling points, we are supposed to put the particles apart from each other by supplying the heat energy as temperature. That is what boiling means, no? Boiling means you are converting the liquid to gas, no? There what will happen? What is happening is actually in a liquid the particles are somewhat close to each other. In a gas the particles are far away from each other. So what you are trying to do here with the boiling is actually you are trying to put the particles apart from each other. That is what you are doing now, right? So for that, the temperature is supplied to supply the energy to do the process now. So basically, the interaction strength matters. You have to break the bonds. You have to break the bonds between the particles to put them apart from each other, right? So the bond strength matter, right? For the boiling as well as melting. Here, when it comes to boiling points, according to practical observation, it seems like that to put the particles apart from each other in water is but harder than that of HF, right? To put the particles apart from each other regarding H2O is much harder, or much more heat temperature should be supplied compared to that of HF. This is the reason. The reason is not because of the strength of the hydrogen bond, but because of the number of hydrogen bonds one particle can form. Number of hydrogen bonds one particle can form. The idea is this. See, I'll just put some numbers. These are not the actual accurate numbers. To explain you the idea, I'll come up with some numbers, right? Let's say, right, this HF hydrogen bond is with kind of a strength with 10 units, 10 kilojoules mole or something like 10 units of strength. So you have two of those, two 10 units stronger hydrogen bonds. As HO bond is weaker than that, I'll take it as 8 units less than 10, no, 8 units. But with water, you have 4 of 8 units hydrogen bonds. So actually to isolate this water molecule, right, you have to supply 8, 16, 24, 32 kilojoules of heat to isolate this water molecule. By breaking these 4 hydrogen bonds, you have to supply 32 kilojoules of heat. But here, to isolate this one, you need to supply only 20 kilojoules of heat to break these 2 hydrogen bonds. So all because of number of hydrogen bonds with the H2O. H2O wins with that. Due to H2O can form 4 hydrogen bonds. One H2O molecule can form 4 hydrogen bonds, right, compared to 2 of H2O, right? So this reason is because the H2O will form 4 H bonds compared to 2 H bonds of HF, right? So H2O wins because of that. Even though the strength of one HF bond hydrogen bond is stronger than the strength of one OH hydrogen bond, still with the boiling point H2O wins, as H2O forms 4 hydrogen bonds compared to 2 of HF. Right now, so that is the idea. So write this thing as well. This is a very important point, right? This will be asked in MCQs. Reason should be also known. Right now, strength of a single hydrogen bond varies like this. HF wins, and this is the NH hydrogen bond. But right, the boiling point variation is like this. Due to more number of hydrogen bonds, one H2 molecule can form. Right now, so normal lamai this boils at 100 Celsius, while the HF boils at 19 Celsius. If you need numbers, this boils at 100 Celsius and HF boils at 19 Celsius. This come up with minus values, right? Boiling point of NH3 is kind of a minus value, right? Okay, now those are the very important stuff with hydrogen bonds appearing with H2O, HF and NH3, right? Okay, this is done. Let's discuss few more stuff about the hydrogen bonds, right? So these 3 are very important stuff, right? Then let's discuss about few more, right? Right. I'll erase that thing as well. Let's come up with few more examples, right? This one, acetic acid, right? Among acidic acid molecules also you can see the presence of hydrogen bonds. See, so this is the acetic acid, right? This is a molecule of acetic acid. Right? So you have a greater negative delta appearing here. Right? Because of electrons of this bond, this pair will be greatly attracted towards the oxygen. You will see a great negative delta appearing here. As electrons here are greatly attracted towards this oxygen, right? Some positive delta will appear here, right? This is the nature of the CH3, right? With some negative here, right? So that will be connected with another CH3COOH molecule. See, this is another CH3COOH molecule. Another one. Sorry, like this. Another CH3, CH3, C double bond OH molecule. Here as well, due to this electron attraction towards this oxygen, greater positive delta appearing here, negative delta here, and as electrons are greatly attracted towards this oxygen here, like this, you have a electronegative atom with lone pair. Electronegative atom with a lone pair. So because of this bond, attraction of electrons towards the electronegative atom, you create a greater negative delta here with this oxygen. Right? And what will happen? You would be able to see some hydrogen bond formation here as well as here. So two CH3COH molecules are connected via hydrogen bonds. Connected via hydrogen bonds, right? So I'll write this thing normally, right? So two CH3COH molecules are connected via hydrogen bonds like this. See the appearance of hydrogen bonds among acetic acid molecules, right? That is how the acetic acid will be appeared at its liquid state, right now. Okay, right. This is about the hydrogen bonds among acetic acid molecules. Just draw this stuff in a knot. Right. You can clearly see this nature here, right? So you have it into atom with a lone pair. Here, neutron atom with a lone pair. And you have a hydrogen which is connected to it atom. Right? See? So there could be hydrogen bond between the hydrogen and the oxygen like that. Here as well, the same scenario. Electronegative atom with a lone pair. And hydrogen which is connected to a electronegative atom. So between the hydrogen and oxygen, you could form a hydrogen bond. Right now, that is about the hydrogen bonding in acetic acid. Right? Let's discuss a very important one, very important special case. Right? A special one. This is E, no? Fifth one. Chloroform. Chloroform is CHCl3. And acetone. Chloroform and acetone. Acetone is this. Among chloroform and acetone, among these two molecules, we could observe the formation of hydrogen bonds. This is a very important case. This is a very VIP case, right? Very important case to study. Let's see why. So chloroform is this kind of a molecule. You have a hydrogen connected to carbon and 3 chlorines are here. This is your chloroform. Right? This is your chloroform. Right? And then the acetone. This is your acetone. Right? Acetone is carrying some lone pairs. It's okay. So you have a H2O atom, which is the lone pair. So this nature is there. That is okay. As these electrons are attracting towards the H2O atom, this will come up with a greater negative charge, greater negative delta. That side is okay. But here, when it comes to this one, this is not a bond containing an electronegative atom. See? So the hydrogen should be connected to a electronegative atom. Normally, these four are considered as the best candidates to connect to the hydrogen. These four ways. See? But remember, you have this other thing appearing here, the other. This is that special example, special situation. See what will happen here. So, the case is, the thing is, actually, you are with 3 chlorine atoms here. So, all those chlorines will attract heavily the electron densities of these bonds towards them. As chlorines are considered as somewhat negative atoms, the third place guys, right? Those will attract heavily the electron densities of carbon. So that the carbon's electronegativity will increase. In this case, it will increase up to the level of the nitrogen. Level. So, electronegativity will vary with the chemical environment, no? Normally, carbon is carrying 2.5. Normal carbon will carry 2.5. But this is not a normal carbon. It is with a high oxygen state. And connected atoms will also decide so electronegativity. So, you are connected to 3 of highly electronegative atoms. So, electronegativity of this thing is high now. Is not the 2.5 further. It will be much closer to the nitrogen's electronegativity. Closer to 3. So, then this pair of electrons will be heavily attracted towards the carbon. Creating a greater positive delta here. Right? Due to this situation, greater positive delta will be created as these electrons will be heavily attracted by this carbon. It is not a normal carbon. It is a carbon which is connected to 3 of greatly electronegative atoms. So electron deficiency of this carbon is very high. So the electronegativity of this carbon becomes high now. So that it will attract the electron density of this pair of electrons greatly towards the carbon, forming a greater positive delta on the hydrogen. So that these two will attract, forming a hydrogen bond. Right? Okay. So it's a special kind of hydrogen bonds where the hydrogen is not connected to one of these. Where the hydrogen is not connected to a highly electronegative, or the one can say it is not connected to a Fonkel. Where the hydrogen is not connected to a Fonkel. Right? So we can write, here we have H bond donor. Here, right? H bond donor other than Fonkel. This is known as chloroform. Chloroform is kind of H bond donor other than Fonkel, right? So it is a very special situation. So it is not a necessary for hydrogen to attach to a Fonkel. It It is not a necessary for hydrogen to attach to a Fonkel, but it is necessary for hydrogen to attach to a highly electronegative atom. Yes, now in this case, the carbon is considered as a highly electronegative atom because its electronegativity is increased due to the 3 bonds with the highly electronegative chlorines. Right now? So again, I am telling you, for hydrogen bonding, it is not necessary for hydrogen to attach to a Fonkel, but it is necessary for hydrogen to attach to a highly electronegative atom. That could be an atom other than Fonkel. Right? So here the carbon is such. Right now? So know this one as well. At the page number 7, you have this space, right? It's very important thing. A hydrogen bonding situation without a Fonkel attached to a hydrogen. Right now? Okay. These are some few examples appearing we can consider when learning about the hydrogen bonds. Right now? Okay. Let's discuss more about the hydrogen bonds. Right? Okay. Right. So, what we have explained or learned so far is all about intermolecular hydrogen bonds. What we have learned so far is all about intermolecular hydrogen bonds. Right? Appearance of hydrogen bonds among molecules, between molecules, intermolecular hydrogen bonds. Among 2 molecules, you would see the appearance of hydrogen bonds. Intermolecular hydrogen bonding, right? That was the discussion up to so far. Now let's discuss about the intramolecular hydrogen bond situation. There's another kind of hydrogen bonds known as intramolecular hydrogen bonds. We'll discuss about that thing as well. Intramolecular means inside the molecule. Hydrogen bonds inside the molecule. We'll discuss about that thing as well. Right? Okay, intermolecular hydrogen bonds and intramolecular hydrogen bonds. Let's differentiate the 2 things and discuss about the variation of melting points due to those. Right. Okay, this is the 2 things. Let's compare the 2 things. Intermolecular hydrogen bonds and intramolecular hydrogen bonds. Intermolecular hydrogen bonds and intramolecular hydrogen bonds. Right. See the difference. Intermolecular means hydrogen bonds between molecules. Intramolecular means hydrogen bonds inside molecules. Right? Inter means between molecules. Intra means inside a molecule. Let's see the difference. So I am calling it paranitrophenol as an example. As an example, I'll take the paranitrophenol. This is the molecule, paranitrophenol. You have NO2, you have an O and an H. and which will be connected to another molecule like this. Right? This is the para-nitrophenol situation. Right? Okay, one can write it as a circle O as well as this, right? Both are same, right? We have minus here and some plus here. The para-nitrophenol. Right. Among these two molecules, you would observe the formation of hydrogen bonds here. How come? Because you have a highly iterative atom and a hydrogen connected to that. So you have a positive delta appearing here and negative delta appearing here like this. And you have a alternative atom with a lone pair. Right? Because of this bond, attraction of electrons from this bond, this will be negatively charged, so that those will ultimately attract with the use of electrostatic attraction as well. Right? So hydrogen bonds among two molecules. Intermolecular hydrogen bonds. Intermolecular among two molecules, the hydrogen bonds appear. Let's discuss about the intramolecular situation. The intramolecular situation. It is like this. Inside the molecule. See? You have this. You have this thing. So I write like this. You have this one, right? And then you have another section. Right, which is supposedly charged here. Right, this one. So one single molecule here, right? One single molecule here is known as orthonitrophenol. Is known as the orthonitrophenol. Right? It's known as the orthonitrophenol. Earlier it was the para-nitrophenol. I write it here. No? Is known as the para-nitrophenol. This is the orthonitrophenol. One single molecule. Even with this one single molecule, you could see this structure appearing. So you have a U22 atom connected to a hydrogen, so greater polarization occur. And here you have U22 atom with lone pairs. So some greater negative delta appearing here. So you would observe some hydrogen bonding among that two sections. This kind of hydrogen bonding inside the molecule, one single molecule, but you see the appearance of hydrogen bonding inside that. It is known as intramolecular hydrogen bonding. Intramolecular hydrogen bonding. This intermolecular hydrogen bonding among two molecules, between molecules. Here, the hydrogen bonding inside the molecule. Intramolecular hydrogen bonds. Right? So these are the two types of hydrogen bonds. Earlier also we had discussed about these things. This is the new kind. Intramolecular hydrogen bond appearing inside the molecule. Right now? Okay. Let's discuss about the consequences appearing with this thing due to the intramolecular hydrogen bonding. Lamai, this point is this. So due to the intramolecular hydrogen bonding, actually the melting points, right? The melting point of this thing is smaller compared to this one. That is due to the intermolecular hydrogen bonding. I'll explain that. Right? The melting point variation. If you think of melting point variation, right? Paranitrophenol is with a greater melting point than the orthonitrophenol. I'll discuss the reason. Right? The reason for this. The reason for this is the presence of intramolecular hydrogen bonding in here. This guy is with intra. This guy is with inter. What happens when intramolecular hydrogen bonds are there? The thing is, Lamai, actually melting points are decided by the strength of interactions between the particles. So at the melting, what we are doing is, we are trying to put the particles apart from each other to convert the solid to a liquid. That is what melting means. Right? To do so, we have to break the bonds between the particles. If the bonds between the particles are stronger, we need to supply greater heat, greater energy as temperature, by temperature. So melting points will be high then, if the bonds between the particles are strong. Right? So when the intramolecular thing appears, what happens is, when the intramolecular hydrogen bonds appearing, what happens is, actually ability to form the intermolecular hydrogen bonds decreases. Because now this hydrogen is used to form intramolecular hydrogen bond. So now this hydrogen can't be used to form intermolecular hydrogen bonds. To connect this molecule to another molecule of the same kind, you can't use this hydrogen to form kind of hydrogen bond. To connect this molecule to another kind of a molecule, you can't connect those two with use of this hydrogen, because this hydrogen is now used for intramolecular hydrogen bonding. So intermolecular hydrogen bonding can't be done with this hydrogen. So the ability to form the intermolecular hydrogen bonding decreases when the intramolecular hydrogen bonding appears. So when the intramolecular hydrogen bonding appears, the strength of intermolecular hydrogen bonds decrease, so that it is easy to put them apart, as intermolecular hydrogen bonds weaken by the appearance of the intramolecular hydrogen bonding. Right? That is the reasoning. So that orthonitrophenol is with a smaller melting point than the paranitrophenol, where you find the stronger hydrogen bonding intermolecular. Right now? Okay, the reason is that. Right? I'll write it here. When intramolecular H bonding present, ability to form intermolecular H bonds decrease. That is the reason. So that the melting points will decrease, so that the melting points will decrease, right? So for the melting points, what matters is the strength of interaction between the molecules. At the melting point, we are supposed to put those molecules apart from each other. So for that, what matters is the strength of interactions between molecules. That will weaken when the intramolecular happens. Right now, okay, that is the idea, right? That is there in your note as well, right? So they have found that the melting point of this thing is equal to 46, while the melting point of this thing is equal to 130. So you see some greater value here as this hydrogen is strong, right? Okay, that is the idea. Okay, so that is there at your page number 8, right now. Okay. Right. Now then we'll discuss about some special observations we observe due to the presence of hydrogen bonding. Right? This is about that. Right. This is about some abnormal properties observed due to the presence of hydrogen bonds. Right. First thing. Right. This is regarding the variation of boiling points of group 15, 16 and 17 hydrides. Let's discuss about this thing. Right? The boiling point variation. Let's concern the boiling point variation of group 16 hydrides. The boiling point variation. Right? At the group 16, right, you have the oxygen, sulfur, selenium and tellurium as elements, right? So I'm going to write the graph the boiling point with molecular weight. See, right? Okay, the trend will looks like this. So no, I'll better write like this. That is the best way to come up with this idea. This is the molecular weight. Right. So if you have to take the origin from here, that's better then. So the trend is look like this. We'll discuss about this trend and reasons for this. This is the trend in variation of boiling points of group 16 hydrides. Right? This is the H2O. This is H2O. And here you have the H2S, H2SC, and H2TE. Hydrogen sulfide, selenium hydride, and the tellurium hydride. Right? Solar wine, normally you see this trend with the increasement of the molecular weight, the boiling points increase. This is the normal trend. This is a normal trend. So the one with the greatest molecular weight should have the greatest boiling point, while the one with the smallest molecular weight should have the smallest boiling point. That is the normal trend. According to the trend, the H2O should have a value here. H2O should stand here. According to trend, the H2O should stand here because it is the one with the smallest molecular weight. But the practical observation is H2O is here. Even though it is with the smallest molecular weight, still H2O is coming up with the greatest boiling point. The reason is the presence of hydrogen bonding among molecules. Hydrogen bonding among molecules. Presence of hydrogen bonds among molecules. So when the molecules are connected via hydrogen bonds, right, it is very hard to put them apart. So boiling means that. Boiling means converting a liquid to a gas. To do so, you need to put the molecules apart from each other. If you are with a stronger bond between the particles, you need to supply greater energy, greater heat energy as temperature. So you need to supply some greater temperature to put the molecules apart from each other. That occurs when you are with stronger hydrogen bonds among your molecules. So H2O, among H2 molecules, you have strong hydrogen bonds. So that you need to supply some abnormal amount of high heat to boil those H2 molecules, to convert the H2 liquid to H2 gas, compared to the other members of your group 16 hydrides. Even though you are with a smaller molecular weight, right, still you comes up with the greatest boiling point. Right? This trend is due to Lamai increasement of the molecular weight. Right? So normally Lamai, it is hard to move the particles now when the molecular weight is high. When the molecular weight is high, it is normally hard to move the particles. Right? Weight is high means the inertia is high. Weight is high, inertia is high. So not keen to move that much, change the motion that much when the weight is high. So that you need to supply some greater temperature, greater thermal energy to move the particles and convert that liquid to a gas. So that is why when the weight increases, when the molecular weight increases, the boiling point increases. That is a normal trend. But even with the smallest of weights, H2O is with abnormally high value due to the presence of hydrogen bonds. Right now, okay. So the abnormal behavior is due to the presence of hydrogen bonds. Right now, this kind of a trend will be appeared with the group 17 as well as the group 15. Right? I'll draw for those two as well. Right? So for group 17 also, the boiling point trend is like this. Right? If you think of the group 17 stuff, right? Here the molecular weight, I'll put it as in W, right? Same kind of situation appears. Right? So HF carrying a greater boiling point due to the presence of hydrogen bonding among the particle. Right? So you have the other guys as well, HF, HCl, HBr, HI. They are the boiling point increases due to the increasement of the molecular weight, right? So these are the group 17 hydrides. Right now? Okay. Normally this value is 100 Celsius. If you want to know this value, this is just 19 Celsius. All the others are coming up with minus values. So if you need the reason for this thing, this increasement, it is due to the increasement of molecular weight. This increasement is due to the increasement of molecular weight. Right now? Okay, so you see the same trend. This is the presence of hydrogen bonds. Right? Even with the group 15 hydrides, I'll draw it here. You see such kind of a trend. Right? With the group 15 hydrides, but little bit of a difference there with the group 15 hydrides, but same kind of a trend will appear. So one can say it's a molecular weight here. Here's 0. With the group 15, all the guys coming up with as negative values. Group 15 hydrides. But anyway, NH3 carrying some abnormal value. So according to molecular weight, NH3 should have the lowest value. But that is not what you observe here. They should have the lowest value, but that is not what you observe. Because NH3 is with the smallest weight, no? So it should have the smallest value, no? But that is not what you observed. Somewhat higher value is there due to the presence of hydrogen bonding among NH3 molecules. Right? The others are like, the other guys are here, the PH3, and you have ASH3 and SBH3. Right? Again, kind of an abnormally high value is due to the presence of hydrogen bonds. As it is with the smallest molecular weight, we should expect it to have the smallest boiling point, but it is not so due to the presence of hydrogen bond. So abnormally high value, right now. So these things are due to the presence of hydrogen bonding among those particles, among the NH3, H2O and HF, right? So you can complete the stuff, right? Just complete the tree, right? This is due to the presence of hydrogen bonding. Right. Okay, let's discuss about some other special observation, right, due to the presence of hydrogen bonding. Actually, now we are going to discuss about the story of your cover page. Right, story of your cover page. Story of ice. Right, story of ice and water. Right. So normally, when it comes to a material, its liquid state is with a lower density than its solid state. Normally for a material, for a compound, its liquid state comes up with a lower density than its solid state. But with water, the case is different. When it comes to water, right, when it comes to H2O, its solid state, the ice, is with a lower density than its liquid state, water. That is why the ice floats on water, as ice is coming up with a smaller density than the water, than the liquid state. Right? Let's discuss the reasons behind that and the role of hydrogen bonding placed there. Right? Okay. Ice floats on water. Ice means solid H2O. Floats on water. Liquid H2O. So this says that density of this thing, this happens because the density of solid H2O is now smaller than the density of liquid H2O. This is a very special situation, no? Normally solids are with greater densities than the liquid phase. But with water, it is not the case. This is due to the presence of hydrogen bonds. Let's discuss what is happening here. Right? It is like this, Lamai. When you are decreasing temperature, let's say you are starting with 25 Celsius, the room temperature. When you are starting with 25 Celsius and decrease your temperature till 0 Celsius, right? What happens is, when decreasing temperature, your kinetic energies of your molecules decrease. So when you are decreasing temperature, that means you are actually getting rid of heat energy of the system. No? When you are cooling H2O, means you are getting rid of the heat energy of the system. No? It's the heat energy of the H2O. No? That means the kinetic energies of your H2O molecules will decrease as you are getting rid of the energy of the system. The kinetic energies of your molecules also decrease. So when you are with a very little amount of heat, that means when you are close to the 0 Celsius, now the molecules will move very slowly compared to the room temperature. When it is at H2O is at the room temperature, the liquid state, the molecules are moving with some speeds. But when it is coming closer to the 0 Celsius, molecules are very slow. Molecules are with very slow movements, as kinetic energy is lost, as decrease in temperature, heat energy of the system. So what will happen? when the kinetic energies are very small, when they are moving very slowly, right, those particles have much more time, those H2O molecules have much more time to form some strong interactions. When you are moving very fast like this, you don't have any time to have some strong interaction. So, but for H2Os, as those are with very small movements, very small speedy movements, as those guys have lost some kinetic energy due to the decreasement of temperature. Now they can form some strong interactions. Much more time, interaction time is there. So at that stage, H2O will form the strongest possible hydrogen bonds among the H2O molecules. So those comes with some special arrangement. The strongest form of hydrogen bonds with H2O molecules comes with some special arrangement. Kind of an arrangement like this. Right? This kind of arrangement like this. Right? The H2O molecules will arrange, right, like this. When the heat is, right, reduced from the system when you are approaching the 0 Celsius. Right? They form this kind of a special structure. Right? H2O molecules will arrange like this. Right? So the hydrogen bonds will be formed like this among H2O molecules. Right? As I said earlier, one H2O molecule can form 4 hydrogen bonds. Those will connect with like this as well. The maximum hydrogen bonds will be formed at that stage, as a very slow movements are there with H2O molecules. They are keen to form the strongest hydrogen bonds at that instance, right? So this kind of hydrogen bonding situation would be there with 4 molecules, right? So one can say around oxygen, a tetrahedral arrangement could be seen, or around a water molecule, tetrahedral arrangement of other water molecules will be seen, can be seen, right, when the H2O forms ice, right? The special thing here is with this structure is the structure of ice. Structure of ice, it is solid H2O, right? The special thing we observe here is actually you could see some more spaces available. Actually 9% of extra space among H2 molecules will be observed when H2O form ice compared to the liquid state, right? When H2O forms the solid state, the ice, compared to liquid state, 9% of extra space will be available among molecules because of this special kind of arrangement with the strongest possible hydrogen bonding available with H2Os, right? So that the density will drop. More free space means density will drop. Density is the mass in unit volume. So with this free space, you have some volume without masses. So mass per unit volume drops. So density drops when you form ice from liquid H2O. That is why the ice floats on water. Right now? So this is considered as a tetrahedral arrangement of water molecules. Around each water molecule, right, you have another 4 water molecules, right? If you take this one, you take this water molecule, right? You have other 4 water molecules connected around it. So tetrahedral arrangement of, see, tetrahedral arrangement of other water molecules. See, there's a water molecule coming from here, coming from here, coming from here, see, and coming from here as well. So tetrahedral arrangement of water molecules around one molecule. That is a special form, right? When it comes to ice. So anyway, that is with some 9% of extra space among molecules. So density will drop compared to liquid H2, right? So this special observation is due to the presence of hydrogen bonding among H2 molecules. That is a consequence of hydrogen bonds among H2 molecules. Right now? Okay. That is all about the hydrogen bonds we should know. Right. Let's quickly move to the next one. Next type of secondary interactions. Let's discuss about the ion-induced dipole interactions. Okay, so basically, ion-induced dipole interactions means, as the name suggests, it should be the interactions between the charged particles that means cations or anions, and induced dipole means those are non-polar molecules, right? So ion-induced dipole interactions are the second interaction kind appearing between the charged particles and the non-polar molecules, right? Charged particles and the non-polar molecules, right? So let's come up with some examples for this one. Let's think of some, discuss about some examples for the ion dipole interactions, right? One good example is this one. So normally, right, when you are trying to dissolve some I2, the I2 is known as kind of a non-polar species, no? I2 is non-polar. I2 is non-polar, right? So if you are trying to dissolve I2 in water, right? Dissolution is not that much, Lama. Dissolution is not that much. I2 won't dissolve in water that much, right? But if you are trying to dissolve that I2 in a solution with Ki, right? If you are trying to dissolve the I2, if you are trying to put these I2 molecules in a solution with Ki, the ions are there. We are trying to dissolve this thing in a solution with Ki, then dissolution happen greatly. I2 will dissolve easily in a Ki solution. Right? Let's discuss how that happens. Right? So dissolving in water means right, connecting with water molecules. Normally by second interactions. Right? Trapped inside water. That is what we meant by dissolving in water. If the particles are trapped inside water, we can say it dissolved in water. If the particle is surrounded by water molecules, we can say it is dissolved in water. For that, it should be able to connect with water molecules somehow. Right? Let's see how these I2 particles are trapped in water when Ki is present. Right? Those are not that much keen to form bonds with water molecules. Huh? So the I2 guys are non-polar guys now. I2 guys are non-polar. So those are not that much keen to form bonds with water molecules. Polar guys. Right? This bond is very weak. Huh? This is very weak. Right? So not dissolves much in water. Right? Let's see how we are supposed to dissolve or trap these I2 guys in water. It is done like this, right? It's done like this. So you are first coming up with a aqueous Ki solution. Then with the aqueous Ki solution, this kind of thing happens. Right? Aqueous Ki solution, this kind of thing happens. In aqueous Ki solution, you have I minus ions. Those are ions. Right? And now you are providing I2. It's a non-polar species. Right? Which is known as an induced dipole. Non-polar species. Right? Non-polar molecule. So when these two guys are mixed, it will form some species referred to as I3 minus. It forms some species referred to as I3 minus. How it is formed? It's formed like this. So you have the I minus. You have the I minus particle. Right? Like this. And when these guys are coming closer to the I minus particles, the electron density of these guys will repel from the minus charge. Electron density of this guy will repel from the minus charge. Right? So that you will form something like this. The I2 molecule. So more electron density here. Bit of electron density here. So you will create a positive pole here and a negative pole here. That is what we say as induced dipole. So one can say this is as the non-polar molecule. Here it's a non-polar molecule. When this thing occurs, it is becoming a induced dipole. Induced dipole. So this is ion. So among this ion and the induced dipole you created, this opposite charge things, right? There you would see the appearance of ion-induced dipole interactions. Induced dipole interactions. That is how the induced dipoles are created, right? When those guys are coming closer to the ions, so electron densities of those things will repel from the negative charges. That is how the ion-induced dipole interactions are formed. So like this, you will form the I3 minus. Like this, you will form the species I3 minus. This is known as the I3 minus. Right? Ultimately, you form the I3 minus. After forming the I3 minus lamine, then you can dissolve in water easily. With this form, it is hard to dissolve, but after you producing I3 minus, by this ion-double interactions, after you produce I3 minus, it will easily attract towards the water molecules with the use of what? With the use of ion-dipole interactions. Right? So now the iodine is trapped. Now the iodine is trapped in water like this. So you have the I minus and I2, right? This is how the I3 minus is formed. This is the ion-induced dipole interactions. So with this, you can think of I3 minus AQ. So it shows easily. I3 minus. It shows easily in H2O, so that I2 will be trapped in H2O. Right now? So that can be done. Right? So I2 dissolves easily in H2O with a solution with I minus. Right? That is the idea. So there you see the formation of what? Ion-induced dipole interactions. Right? Here the ion-induced dipole interaction, here the ion-dipole interaction. So this is a neutrally charged. This is ion dipole. This is ion-induced dipole. This is ion dipole. Here you have the ion-induced dipole. Like that, you can dissolve the H2 in water, right, forming I3 minus. So you can come up with this example, right? You have this example in your note, right? So that is some more stuff about the same scenario, right? Now this is all about the ion-induced dipole interaction, right? The third kind of interactions we have learned today. Third kind of second interactions, right? Okay, right. Let's discuss about the fourth kind, the fourth type of second interaction. The fourth kind of second interaction, right? That is the dipole, induced dipole, dipole-induced dipole interactions. Dipole-induced dipole interactions. Right? As name suggests, this is the second interaction between the polar molecules. The dipoles are the polar molecules, right? Polar molecules and non-polar molecules. Induced dipoles are the normally non-polar molecules. Among the polar molecules and the non-polar molecules, if there is a second interaction occurring, that is the dipole-induced dipole interaction. Dipole-induced dipole interactions. Alright? So normally, we can see these kind of interactions when the non-polar species dissolves in water. Right? We can observe these kind of interactions when non-polar species, let's say non-polar gases dissolves in water. Right? You know, the O2 gas dissolves in water to form the O2 aqueous. That is due to this interaction. Right? The Cl2s, non-polar gases, will dissolve in water. CO2 will dissolve in water due to this kind of interactions. See? So you have water molecules, right? So if you are to think of like this, if you have water, if you are dissolving some O2 gas, so water is polar molecule, this is non-polar, this is non-polar. So non-polar gas is dissolved in water due to these interactions. See? So you have water, guys, and then you have O2, the non-polar guy. This is polar molecule, non-polar molecule. So polar guys are known as dipoles. Non-polar guys are known as, can be referred to as induced dipoles. So when you are trying to dissolve this one, what will happen? First of all, when this guy approaches, right? When this guy approaches, let's say to the positive delta terminal, let's draw this one like this. Let's draw the situation like this. When this guy approaches the positive delta terminal of oxygen, what will happen? The electron density of the symmetric electron density of this oxygen will come more towards that, attract heavily towards that, to the positive terminal of this thing. So ultimately, you will produce something like this. To the positive terminal, the electron density will be attracted. And with the O2 ultimately, you would observe some greater electron density appearing here and less density here. So some negative delta here, positive delta here. So that is what we refer to as the polarization of the non-polar stuff. Now we are with the induced dipole. Earlier it was a non-polar one. Now we are with the induced dipole. So this is a dipole. Polar species is kind of a dipole. So between these two guys, the second interaction form is known as the dipole-induced dipole. Right now? So always the non-polar gases dissolve in water, forming these kind of interactions. Right? Cl2 dissolves in water using this because water is polar. Cl2 is non-polar. Polar means dipole. Non-polar means induced dipole. Dipole-induced dipole interactions. Right? CO2 will dissolve in water using dipole-induced dipole interactions. Right? So not only dissolving in water, right? Any of non-polar species will dissolve in water, so dissolve in polar solvents with the use of these interactions. Dipole-induced dipole interactions. If you need some more examples, so you can think of HCl. You can think of HCl, right? And the argon. HCl and the argon. So argon is with a symmetric electron density. HCl is kind of a polar molecule, having some poles. This is a non-polar molecule. Then when those two guys comes closer to each other, what will happen? The electron density of this thing will repel from the negative charge of Cl minus, so that you will ultimately end up with something like this. Some small electron density near the chlorine, some great electron density at the other side. So it will create some poles here, right? So this is a dipole. This kind of induced dipole. So among these opposite charges, the dipole-induced dipole interactions will form. Right now, that is how you are supposed to form the dipole-induced dipole interactions between the polar molecules and non-polar molecules. Right now? Okay. Normally, when it comes to these dipole-induced dipole interactions, right, that the strength of that thing will depend on these two charges. So that these two charges will depend on the charge of the polar molecule will depend on the electron difference or the strength of dipole of this thing, and charge of this thing, charge of the non-polar species, this one, will depend on its polarizability. Greater the size with you, the polarizability will be high, so the charge will be high. So the strength of dipole-induced dipole interactions will depend on the dipole moment of the polar molecule as well as the polarizability of the non-polar molecule. If the dipole moment of the polar molecule is high, then this delta is high. If the polarizability of this thing is high, then this delta will be high, so that the attraction will be heavier, right? So when the dipole moment of the polar molecule is high and the porosity of the non-polar molecule is high, your ion dipole interaction strength will be high, right? That is also indicated in your note. Let's go to that right now. Okay, with this thing, right, we'll wind up the session for today, right? At the next lesson, we are trying to complete the unit 2, right? There we'll learn about the London forces, the 5th kind, and some more stuff regarding the lattice structures, the melting points and the conductivity and stuff, right? With that we'll wind up the session, but not today, at the next day, right? So after then, goodbye then.